what species are going to be produced and how much of it is going to be produced. And that's how these experiments are very, very important. So this is basically what it is. And what do you mean by annealing? Annealing simply means that once you have deposited the whole thing, you can record a spectrum, then you heat it to 40K. So the initial experiment is done at 10K. You heat it to about 40K. Why 40K? Because I can't go above 40K. If I go above 40K, the argon vaporizes. Because argon has a vapor pressure which is about 10 to minus 6 to at 10 at 40K. And the confining pressure in the vacuum system is 10 to minus 6. So it will simply boil off. So you can't go above 40K. If you go up to about 40K, what happens at 40K? Because I have given it some thermal energy, the species that you deposited will start to move. And when they start to move, they might form more clusters. A UO and a UO might meet together and form something very exotic. Just to see what happens, we always anneal the system and we see what happens. So annealing is a process by which you take your sample, you heat it to a temperature, you keep it there for about half an hour, 1 hour, 2 hours. These are experiments where we kept it for about 8 to 10 hours. And then went back 10 Kelvin, recorded this experiment, recorded the spectrum. In the process, hoping that the diffusion will give rise to further new features that we might encounter in these experiments. The last experiment was done in argon. Then we said, just for the heck of it, let's take uranium oxide and trap it in nitrogen. So instead of passing argon to the experiment, we pass nitrogen to the experiment. And all the reactive species that were produced as a result of the laser ablation process were now trapped in nitrogen. And again, we got many of these species. And again, I won't go to the assignment. Again, you get UO, UO2 and all that. But that's not the interesting part. The point is we get all these different species, which are high temperature species, produced at 4,000, 5,000 Kelvin as a result of the laser ablation process.
So, why does the spectrum in oxygen show a much different annealed structure as compared to
in argon? This one?
In nitrogen, yeah.
No, this one.
Yeah. Why are they so different?
We will, very soon you will see that. Because in the last case, I was taking uranium oxide and ablating this, I get oxide species. When you do it in nitrogen, which is what I'm going to talk to you about next, these species react with nitrogen. And even though we say nitrogen is very inert, these are high temperature stuff. I mind you, at high temperature, anything and everything will react. And therefore, you now have a reaction between the uranium oxide species and the nitrogen, producing nitrites for you. That's basically what is happening. So he's already put the cart before the horse. So we will see this. So what we did now, therefore, we realized that the question that Sri asked, moment we looked at it, maybe there's a reaction going on with nitrogen. So let's make the problem simple. We won't take uranium oxide, we will take uranium metal, ablate that in the presence of nitrogen and see what we get. So what we did was we took nitrogen in argon. So we had argon and we had small amount of nitrogen mixed with that. So that nitrogen now is a reagent. It is no longer a matrix, it's a reagent. And we kept increasing the concentration of nitrogen from 0.1% to 1% to 5% to 10% and finally pure nitrogen when it is a matrix, and this is the experiment I showed you earlier. So to understand that, what we did was we basically did argon experiments in which we mixed very small amounts of nitrogen to see what the nitrogen really does. When you had a small amount of nitrogen, you had one peak out here. It's about 1051. Don't worry about the number, we had a peak. But if I increase the nitrogen, there's one more peak that shows up. For increase the nitrogen further, many peaks. By the time you get to 10%, you have like a 5-figure pattern. But then you go to pure nitrogen, the whole thing collapses to 1. So there is something that's really happening, and that's what we thought should be examined. When you go back and look at the literature and see what has been already done, this turns out to be a perfect assignment for uranium dinitride, UN2. So what is it telling me? That if I take uranium, hit it with a laser, what am I going to get? I'm going to get extremely energetic uranium atoms in the gas phase. And this extremely energetic uranium atom will react with nitrogen and give me uranium nitride. So that sounds reasonable. What about this fellow here? And this fellow over here is basically, I think there is some problem with the way I've assigned it. The extra peak that I get is basically uranium nitride, alright, but now interacting with another nitrogen molecule through a very weak interaction. Like when we talk about hydrogen bonding interaction and so on. So here I have UN2 interacting with nitrogen, and because of which the infrared frequency shifts a little. What happens when I go further? I have one more. It's uranium nitride with 2 nitrogens. Why am I getting 1 nitrogen here and 2 nitrogen here and so on? Because because I've increased the concentration of nitrogen, there's a greater probability that every uranium nitride can have more than one nitrogen sitting around it. So if I keep increasing that, what do you expect to happen by the time you get here? So this is how the species will look. This is how this species will look. Uranium nitride with 2 nitrogens on either side. So the question that follows, by the time I get here, is it simply uranium nitride in nitrogen cage with 6, 8 nitrogen sitting around it? But then there is complete uranium, nitrogen around. There is no way you can have 1 nitrogen or 2 nitrogen. It must be just uranium sitting in a nitrogen cage. And therefore you have one species. Seems like a good argument. That what I am actually doing, going from here to here, is producing uranium nitride with 1 nitrogen sitting, 2 nitrogen sitting, and so on. And by the time you get to this, it's just uranium nitride sitting with nitrogens all around it, very uniform. There's only one species you can think of, which is uranium nitride sitting in a nitrogen cage. The problem came, and this is what it might look like in the cage. However, the problem came when we annealed it. What was annealed? Taking it to body K and see what happens. When you annealed it, see what happens. 0.1%. You had something that was gone. We couldn't even see it. And you'll see why. 1%. You got something. 2%, 5%, 10%, and so on. But see this feature, which we thought was due to the nitrogen cage. What is this feature really? It is simply uranium nitride, 1 nitrogen, 2 nitrogen, 3 nitrogen, 4 nitrogen. It's the same family. So therefore, if you anneal it, there is no reason for this feature to behave differently. It should have behaved just the way every other feature behaves. Like this fellow is more intense with this, the intensity drops, and it should have been even lower. But that's not what it is. Suddenly we find on annealing, this fellow is much bigger than all the others. Whereas over here, it's much smaller. But this very small peak on annealing suddenly became very big at the expense of all of the others. So which clearly told us that this feature over here must all belong to one family. There's a difference of behavior in these two, and therefore this last peak that we saw, which was at 996, this doesn't belong to the entire family. It said when you anneal it, suddenly its intensity shoots up, whereas all the others behave in a certain fashion. In other words, it's highly unlikely that the last feature that you are seeing is simply an extension, meaning it's not just uranium nitride with 1 nitrogen, 2, 3, 4, 5, 6, but if it is a simple extension, all these should have behaved in a very similar fashion. Somehow the last one seems to be behaving very differently, and therefore something must be happening when you have large amounts of nitrogen. It is not simply a uranium nitride sitting in a cage of nitrogens around it. It is not a simple extension of all these other experiments. So we therefore said it probably belongs to 2 different species. This must be a different species altogether, and that is the reason why it is having an entirely different behavior. The question then was, we said, can this be due to uranium dinitride? And this is maybe due to uranium nitride. Why did we see it as uranium nitride? Because it is known that uranium nitride has a peak somewhere in this region. And therefore we believe that what we might be doing is producing uranium nitride also in this experiment. But what's the paradox? The paradox is you're producing UN2 at low concentrations and UN at high concentrations. You don't get the higher nitride at higher concentration, lower concentration. Normally you would have thought at low nitrogen concentration I should have got UN, at high nitrogen concentration I should have got UN2. But here is an experiment which clearly tells us that at low nitrogen concentration you produce UN2. You increase it a little bit, it is UN2 with 1 N2. A little bit more is UN2 with 2 N2s, and so on. And suddenly somewhere at some point you are producing UN all of a sudden. In other words, the reaction actually changes track at some nitrogen concentration. These are the funny things that happen at high temperatures. And that's the reason why I'm mentioning this. So the question is, there's a paradox and you have to come up with an explanation. So we said that the UN2 production is essentially this. You laser ablate uranium atoms are produced, they go screening out. They meet nitrogen, they literally harbor into nitrogen and form NUN. You have your UN2. Simple. How is UN produced? Here is our theory. There are a lot of nitrogen around because you have increased the nitrogen concentration. There is a lot of nitrogen around. And what can happen is the nitrogen can actually collide with uranium. One thing that can happen is with NUN. The other thing that can happen is uranium plus nitrogen collision will simply excite the nitrogen to an excited state. So you have an excited state nitrogen. If you have lots of nitrogen going around, then you can have quite a bit of the excited state population. If you have quite a bit of the excited state population, you can actually think think of a reaction which is N2 star plus N2 star. Now these reactions are not going to be favorable if your nitrogen concentration is low. But if the nitrogen concentration is high, then it is quite possible that you have enough nitrogen going around, enough excited state population of nitrogen, and therefore enough collisions between N2 star and N2 star. And this reaction may therefore become probable by the time you go to high nitrogen concentrations. And when that happens, you have N3 dot and N is a possibility. And this reaction is known to occur. The energetics of the reaction has been worked out. And if you have this in excited states, then this reaction can actually occur. We, in fact, took data of all these and showed that it is thermodynamically feasible to be able to produce these species if you have this nitrogen in the excited state. The nitrogen in the ground state cannot do it. But nitrogen in the excited state can actually push this reaction. Now once you have this can react with uranium to give me UN. N3 dot plus U can give me UN plus N2. Or U plus M can actually give me UN. So now I can actually produce UN. But why am I producing UN? I am producing UN because I have produced N3 and N dot. And why have I produced N3 and N dot? Because of the reaction N2 star plus N2 star. So which means the whole precursor for the process has to be availability of excited state nitrogen. If I have excited state nitrogen in sufficient quantities, then I can do it. But I can't get excited state nitrogen in sufficient quantities unless I have large amounts of nitrogen to begin with. That is the reason why this probably occurs at high nitrogen concentrations. It does not show up at low nitrogen concentrations. So when I keep increasing nitrogen concentration, initially I get this nitrogen simply attaching itself to uranium. But beyond a certain point, I'm actually opening up a new reaction channel. And when I open up a new reaction channel, that reaction channel actually produces for me uranium nitride. That's the reason why low nitrogen concentrations, UN2, high nitrogen concentrations, UN. So it's not really that much of a paradox if you really go back and try to analyze this. Of course, this is only a theory. This is only a reaction mechanism that we have proposed. How do you prove it? Well, if this is really going to happen, then you must be able to trap N3 in your matrix. Of course, you can't study N with infrared spectroscopy. You need at least 2 atoms for vibration. So atomic species will not give you any vibration. Well, it turns out that N3 plus U, the more favorable reaction is UN plus N2, because N2 is a very stable species. Yeah, so you will get UN plus N2, so that's basically what you will get. To get UN2 plus N, it's hard, because you're now leaving behind the reactive species. So this will react with uranium to give you UN plus N2, this will react with uranium giving you UN, but if this reaction mechanism has to be proved, then you must show that in your experiment, you're also trapping N3 in your matrix somewhere. Because if I'm producing N3, it must be trapped in the matrix, and therefore I must be able to show in my experiment that I'm seeing N3 somewhere. If I show that N3 is present, then I know this mechanism really works. So we went looking for N3. In other words, looking at kinetics, the first order dependence on the nitrogen concentration, whereas this has a second order dependence on nitrogen concentration. If you have a second order dependence, quite naturally, you need more of the material to rush your reaction. In the first order, you can get away with low concentration. Then we know all that. So that sort of explains phenomenologically as to what you might actually see. But then the proof of the pudding really is going to be in us being able to show that N3 was actually produced. If you can show N3 was produced in the experiment, then this reaction mechanism is actually quite tenable. So at high nitrogen concentration, IR features of N3 were also seen. For example, when we went and looked back, here is this nice feature that you see at about 1657, which is actually due to the N3 radical. So at high nitrogen concentration, we were actually trapping N3 radicals. And since N3 radicals were there, the mechanism we showed earlier must be right. And if N3 radicals were present, then of course uranium can react with it to produce from a UN at high nitrogen concentrations. And this of course was really what sealed it for us, and we were able to show that yes, if you increase the nitrogen concentration, you really open up a new reaction channel which produces for you UN. So it is not that paradoxical to say that high nitrogen concentration gives you a lower nitride, and that lower nitrogen concentration gives you a high nitride. But what's the genesis for all of this? It is excited state N2 doing this. In other words, it's excited state chemistry that has given you something that's quite paradoxical. And this is what I meant right at the beginning when I said that high temperature chemistry can really throw up some surprises, because we are dealing with not ground state molecules, we are dealing with excited state molecules in the whole process. This is of course just to show that you don't see the entry at low nitrogen concentrations over here, but the moment you go to 100% nitrogen, you see this. This is of course the same spectrum I showed you earlier, and you see this very clearly at large nitrogen concentrations. You don't see that at the low nitrogen concentrations, meaning you need nitrogen star collisions to be able to produce these reactive nitrogen species, which in turn can produce for you the UN species. But now you see what the annealing is doing. So when you're doing the experiment, N3 is sitting somewhere, uranium is sitting somewhere. And then as you anneal, these guys move, and uranium reacts with N2 and produces UN3. And that's the reason why the one peak was going out of bounds, while all of the peaks were sort of behaving in one fashion. There was one peak that was actually building up in its intensity at high nitrogen concentrations. Simply because you were actually trapping N3 in sufficient quantities as a result of the excited state chemistry of nitrogen. Therefore, you want to summarize this laser ablation matrix isolation throws open seemingly unconventional and interesting chemistry. It's unconventional because it's dealing with high temperature chemistry, which involves excited states. It doesn't involve ground states. Because you must remember that conventional chemistry or the laboratory chemistry actually involves ground state chemistry. Even if you're dealing with, let us say, boiling something at 100, 200 degrees, you're really not looking at excited electronic states. Maybe you're increasing maybe some rotational contributions and vibrational contributions to some extent. You're still looking at ground electronic state in all your reactions. But when you do high temperature chemistry the way I just described, you're actually looking at chemistry that is driven by excited state species. Laser ablation also offers the other advantages. Easy method, say the same thing all over again. It's containerless and easy experimentation and no container contamination. As I said, very small amount of samples are required. So somebody gave me about, let's say, 50 milligrams of uranium oxide. They can do a high temperature experiment on this. No problem. You can make a small pellet of that, put it in there and do it.